Today we're going to talk about arithmetic sequences in series, and our objective is to explore and utilize the arithmetic sequences in series. So yesterday we talked about sequences in general, and we said that they were a string of numbers that follow a particular pattern, and that pattern can either be explicit in the definition or recursive. With the explicit, we can plug the term number in, we can get the value out. With recursive, we have to find the next term by using the term before it. Now we're going to talk about a formal definition for a series, and a series is the result of adding all of the terms in a sequence. And then an arithmetic sequence is a sequence in which each term differs from the preceding term by a constant amount. This constant amount is called a common difference. So if we look at an example where our sequence is 2, 6, 10, 14, 18, we can see that the common difference is 4 because we're adding 4 each time. So if we were going to graph that, then we'll go down here. Our a sub n, or our n values go here, our term numbers, and our a sub n would be our dependent. These are tiny, so I'll count by 2s on the n-axis. And then by 1s on the a sub n. And then we can go ahead and plot these points. 1, 2, 2, 6, 3, 10, 4, 14, and 5, 18. And what we can see is that this appears linear. And that our d value of 4 would equal the slope. The difference between an arithmetic sequence and a linear function is really most evenly seen, or most obviously seen, if we were to focus on the y-intercept. A line would have a y-intercept somewhere down here. The problem is that this point is outside of the domain of a sequence because it has an n value of 0. So we can still write a general formula for our sequence, but our arithmetic sequence. We just have to be a little creative. If this were a line, we would say that a sub n would be -2 plus 4n. And I'll show you the exact formula in a moment. But first, let's do another example. So we want to write the formula for the nth term in this sequence. All right, so if we imagined, we know that our d is -3, because we're subtracting 3 each time. And essentially our a sub 0, which doesn't really exist, would be 17. So we can say that a sub n is equal to 17 minus 3n. Or if we wanted to start with the 14, then we would just have to subtract 1 from our n value. So that when we put in 1, we start with the 14. So either of these work here. To find a23, we can use this explicit definition and say 17 minus 3 times 23. Which gives us -52. As I said in the last slide, our arithmetic sequence is normally defined so that we can just plug in our n value and we don't have to worry about that a sub 0. So we'll say that a sub n is equal to a1 plus d times n minus 1. Where d is our common difference. All right, so if we look at the next example, we want to find the 8th term of an arithmetic sequence whose first term is 4 and whose third term is -10. So we'll use the formula here. We know that a3 is going to be equal to a1 plus d times 2, or 2d. We can substitute the values for a1 and a3. So negative 10 is equal to 4 plus 2d. Solving for d, we get that d is negative 7. Then to find the 8th term, we plug in our first term, we subtract 7, and then we put in 8 minus 1 because our n value is 8. And our 8th term is negative 45. So looking at the next example, data shows that in 2010, 64% of the US population was white. So on average, this is projected to decrease by approximately 0.45% each year. And we want to write a formula for the nth term of the sequence that describes the percentage of US citizens that will be white n years after 2009. So since 2010 is the first year after 2009, our 64% becomes a1. So an is 64. And then it's decreasing, so minus 0.45 times n minus 1. And we can leave our formula like that. We don't have to do any more arithmetic. But then we can use it to determine the percentage of the US population projected to be white in 2030, which means that 2030 is 30. So 2030 is 21 years after 2009. So then we'll use that as our n value and say that a21 is equal to 64 minus 0.45 times 21 minus 1. If we type that into the calculator, we get 55%. All right, moving on to a new idea, which is the sum of a finite arithmetic series. So we're going to add up the terms in a arithmetic sequence. And if you ask me in class, I'll tell you all about our friend, the 10-year-old Carl Gauss, who gave his teacher fits. But in an interest of keeping the video a little bit shorter, I'm just going to give you the general formula right here and say that this is something you definitely need to memorize. All right. T sub n or a sub n, so T1 is the first term in your arithmetic series, and Tn is the last term. So we can find the sum of the first 25 terms in this series. The first thing we want to do is check to make sure that it is in fact arithmetic. So is there a common difference when we go from 11 to 14, 14 to 17, 17 to 20? The answer is yes. Fabulous. We know that D is equal to 3. And so to use this formula, we would say that S25 is equal to 25 times 11. That's our first term. But we don't know our 25th term out here. We can find it by using our arithmetic sequence formula and saying that A25 is equal to 11 plus 3 times 24, which means that our 25th term is 83. Now that we know the last term in our series that we're going to add up to, we can plug that into the formula, divide by 2, and if we were to add all of those numbers up by hand or using a calculator, we'd get 1,175. We can also check with the graphing calculator. So even though each term of the series can be written explicitly, we write the sum recursively, okay? So when we write it recursively, remember that in the graphing calculator, we have to have our recursive definition, so un minus 1, and then the explicit portion for how we get each new term in the sequence, and our initial value. If you do that and you want to check, then you would hit second and the graph button to find the table, and you can scroll down to 25 and you'll get the same answer. Okay, last question of the day. Your grandmother has assets of $500,000. one option that she is considering involves an adult residential community for a 6-year period beginning in 2020, and the model is given by that expression. And that's describing the yearly costs for the years after 2019. And so the question is, does she have enough to pay for the facility over that 6-year period? So, the things we need to know. 1, that in the first year, A1 is $65,930, and that in the 6th year, she would pay $74,930. But we need to make sure that she has enough money to pay for all of the years. So we're really looking for the sum over that 6-year period. So we'll say S6 is equal to 6 times the 65,000 and the 74,000, and just change over 2. And if we type that into the calculator, we discover that over 6 years she'll pay $422,580. So just barely, yes, she has enough money to last 6 years in that particular facility. But I don't know that she would really make it a 7th. All right, let me know if you have any questions.